Hi students, as a part of IR spectroscopy, today I am going to explain you the very important topic. Very important topic, that is total number of vibrations in a molecule. Total number of vibrations in a molecule or vibrational degree of freedom. That is, whenever the IR radiation is irradiated on the molecule, how many vibrations are possible in each and every molecule? In each and every molecule, that is total number of vibrations in a molecule. I'm going to explain you that. So for calculating the total number of vibrations in a molecule, the molecules are broadly categorized into two categories: linear molecules and non-linear molecules. Linear molecules and non-linear molecules. And in order to calculate the total number of vibrations in linear molecules, one formula has been formulated. That formula is 3n minus 5. 3n minus 5. And in order to calculate the total number of vibrations in non-linear molecule, another formula has been formulated. That is 3n minus 6. What is n, everything, what is 3, I will explain later. But students, have you ever thought that why only 3n minus 5 formula should be used to calculate the total number of vibrations in linear molecules? On the other hand, why only 3n minus 6 formula should be used to calculate the total number of vibrations in non-linear molecules? Is it a myth, students? It is a fact. Right? So whenever it is a fact, we have to know why only 3n minus 5 formula should be used to calculate the total number of vibrations in a linear molecule, and 3n minus 6 formula should be used to calculate the total number of vibrations in non-linear molecule. You have to know why these formula came into picture for calculating the total number of vibrations for linear and non-linear molecules respectively. So accordingly, what I mean to say is, this particular video is very important in order to have the complete grip or total grip on the IR spectroscopy. You have to watch this video until the end. Because this is the basis for IR spectroscopy. I am going to discuss why 3n minus 5 is the formula should be used to calculate the total number of vibrations in linear molecules, and 3n minus 6 formula should be used to calculate the total number of vibrations in non-linear molecules. I am going to explain that only. So you have to understand the concept behind. So even I can say 3n minus 5 is the formula used to calculate the total number of vibrations in linear molecules. Now I will give some of the linear molecules and I will incorporate or substitute the values into it. I will get the value. So total number of vibrations, you will get it. But why this formula is being used? That you have to know. Right? So for that, I am going to explain. I am going to start this video with the degree of freedom. I am going to start this video with the degree of freedom. So now, what is the degree of freedom? What is the degree of freedom? The number of directions in which the molecules can move freely. The number of directions in which the molecules can move freely is called as degree of freedom, and it is represented by capital F. It is represented by capital F. So basically, any of the molecule can move in 3 directions: X, Y, and Z. X, Y, and Z. So why I have depicted this, you will come to know later. So that is the definition of degree of freedom, the number of directions. Now the degree of freedom are of three types, students. The degree of freedom are of three types. The one is degree of freedom of transitional vibration, which can be represented by Ft. Second one is degree of freedom of rotational vibration, which is represented by Fr. And third one is degree of freedom of vibrational motion, which is represented by Fv. So first one is degree of freedom of translation motion, represented by Ft. Second one is degree of freedom of rotational motion, which is represented by Fr. And third one is degree of freedom of vibrational motion, which is represented by Fv. Now we have to discuss one by one. So first what is it? Ft. That is degree of freedom of translation motion. So the name itself implies. So these are produced by translation motion of the molecule. These are produced by translation motion of the molecule. And maximum number of this type of degree of freedom, that is degree of freedom of translation motion, which is represented by Ft, is 3. Maximum is 3. Because 3 directions, so maximum will be 3. Because the transitional takes place in y-axis, x-axis, or y-axis or z-axis. So maximum is 3. And this value is 3 for all the molecules. Whether the molecule is monoatomic molecule, or diatomic molecule, or polyatomic molecule, or linear molecule, or non-linear molecule. Irrespective of the molecule, do remember that the degree of freedom of translation motion is 3 for all the molecules. 3. Ft means 3. That's it. For all the molecules. And these are present at ordinary temperatures. These are present at ordinary temperatures. These are present at ordinary temperatures in all the molecules. I hope you understood this. Now coming to the second, degree of freedom of rotational motion, represented by Fr. So these are produced by rotation. These are produced by rotation of the molecule about an axis. Rotation of a molecule about an axis passing through center of mass of the molecule. These are produced by rotation about an axis, passing through center of mass of the molecule. And their number depends upon the structure of the molecule. We cannot say that it is 3 or 2. So that is decided only by seeing the structure of the molecule, whether it is linear or non-linear. It is not constant, just like Ft, translation motion. So translation motion is constant for all. It is 3. Why it is 3 already explained. And these are also present. This motion is also present at ordinary temperature. This is also present at ordinary temperature. Now coming to the most important degree of freedom from the IR spectroscopy perspective is a degree of freedom of vibrational motion. Which is represented by Fv. So these are produced by vibrations in the molecule. And their number depends upon the structure of the molecule. Their number depends upon the structure of the molecule. If it is linear, one value. If it is non-linear, another value. Do you remember that? This is not present at ordinary temperature. These are produced only at high temperatures. This is very, very important point. These are present in all the molecules at ordinary temperature. That is Ft, degree of freedom of translation motion is present at ordinary temperature. Next, degree of freedom of rotational motion, which is represented by Fr, is also present at ordinary temperature. But degree of freedom of vibrational motion, which is represented by Fv, is only produced at high temperatures. Whenever the high temperatures is subjected, whenever the high temperature is supplied to the molecule, then only this particular degree of freedom is possible in the molecule. I hope you got it. Now, we have to discuss about these first, about Ft and Fr. Why? Because these are present at the ordinary temperature also. This is only produced at high temperature. So, first we have to discuss about this Ft and Fr. If we take linear molecules, we take a linear molecule. So formula is F is equals to Ft plus Fr. Ft plus Fr. We are not discussing about this. Why we are not discussing? This is only produced at temperature. But these are present in the molecule even at ordinary temperatures. So that's the reason we are discussing about this. So for linear molecule, F is equals to, already I have discussed, the degree of freedom of translation motion, which is represented by Ft, is common for all the molecules irrespective of their structure, whether it is monoatomic, diatomic, polyatomic, linear or non-linear. Its maximum value is 3. It is constant. Already I have explained. 3. Now coming to Fr, degree of freedom of rotational motion, which is represented by Fr for linear molecules. So in the case of linear molecules, students, the molecule can rotate only in these two ways. Right? Perpendicular, right? This is horizontal, this is vertical, only in two ways. Linear molecule can rotate only in these two ways, right? Perpendicular along the axis, passing through center of mass in two directions. This is first direction, this is two direction. Second direction. Passing through center of mass in two directions only. So Fr for linear molecule is 2. So Fr for linear molecule is 2. So accordingly, F is equals to 5. So the number of degree of freedom for linear molecule is 5. This is for linear molecule. So coming to non-linear molecules. F is equal to same. So we are not discussing about IR spectrum perspective, because This Ft and Fr is possible at the ordinary temperature. This is not possible at ordinary temperature. We are now discussing at ordinary temperature. F is equal to same Ft plus Fr. So F is equals to, already have said, degree of freedom of translation motion, which is represented by Ft, is 3 for all the molecules irrespective of their structure, and rotations also 3. Non-linear molecules. So rotation is also 3. So degree of freedom of rotational motion, which is represented by Fr, is also 3. So F is equal to 6 students. F is equal to 6. So number of degree of freedom, I hope you got it. Number of degree of freedom for linear molecules is 5, whereas number of degree of freedom for non-linear molecules is 6. Number of degree of freedom for non-linear molecules is 6. I hope you got it. Number of degree of freedom for a linear molecule, under normal case, we are not considering the degree of freedom of vibrational motion into account. Right? So F is equals to 5. For non-linear molecules, whenever the last degree of freedom is not considered or taken into account, then F is equals to 6 strokes. F is equal to 6. Now, let us apply the concept what we have discussed till now to the IR spectroscopy. Let us apply the concept till now what we have discussed to the IR spectroscopy. Now, do remember students, F is equals to 3n, basically. F is equal to, F is nothing but degree of freedom. What is 3? Already discussed. Right? Already discussed. 3 is number of directions in which a molecule can move, freely move. So how many directions? Basically 3 directions, x, y and z. So that is the reason 3. That is the reason 3. So 3 directions, 3. 3 directions, 3. Now what is n now? N is nothing but number of atoms in a molecule. Number of atoms in a molecule. Number of atoms in a molecule. Now instead of from now I will write 3n. Now we are going to consider the IR spectroscopy. We are going to apply this concept to the IR spectroscopy. In the IR spectroscopy, we are using the IR radiation. IR radiation is what? Heat radiations. So heat radiations are hot. So under the hot conditions, even third degree of freedom is also possible. That is degree of freedom of vibrational motion, which is represented by Fv, is also possible. So accordingly, F is equals to what? 3n is equals to, this is for IR spectroscopy. Whenever IR radiation is passed on the molecule, then 3 motions are possible. Under normal conditions, only 2 motions, translation motion and rotational motions are possible. But whenever we supply the heat to the molecule, then 3 motions are possible in the molecule. Transition motion is possible, rotational motion is possible, and vibrational motion is also possible. F is equals to 3n equals to Ft plus Fr plus Fv. Now for linear molecules, friends. For linear molecules. So F is equal to 3n equals to, for linear molecules, Ft plus Fr. Ft plus Fr was 5. Ft plus Fr was 5. 5 plus Fv. What we want? The total number of vibrations in a molecule. That is, we want a degree of freedom of vibrational motion, which is represented by Fv. We want Fv. By rearranging the equation, what will get? Fv equals to 3n minus 5. So this is the reason we have to follow 3n minus formula to calculate the number, the total number of vibrations in linear molecules. This is the reason. Okay, got it. So coming to non-linear molecule. For non-linear molecules, same. F is equal to 3n, so 3n equals to Ft plus Fr plus Fv. So 3n equals to, for non-linear molecules, what is the value of F? F equal to 6. So 6 plus Fv. So what we want? Fv equals to 3n minus 6. So this is the reason we have to follow Fe equals to 3n minus 6 formula in order to calculate the total number of vibrations in non-linear molecules. This is the reason why we have to follow 3n minus 5 formula for calculating the total number of vibrations in linear molecules. So it is not a myth, students, it is a fact. So you have to know the fact, right? So formula is there, you have substituted the value and you got it. What is the reason? What is the reason? You should understand the concept, right? Why 3n minus 5 should be used for linear molecules? Why 3n minus 6 should be used for non-linear molecules? In order to calculate the total number of vibrations. Why not the scene is reversed? Why not the other formula? I hope you understood this concept. Where 3 is total number of directions and n is number of atoms in the molecule. So now it is very easy for you to calculate the total number of vibrations in any of the molecule. Now there is no need to memorize 3n minus 5, 3n minus 5, 3n minus 5 for linear molecules, 3n minus 6, 3n minus 6, 3n minus 6 for non-linear molecules. Very easy, right? Because you have the concept. So this is the beauty of concept, right? So please try to understand each and everything, every topic conceptually. Thanks for watching.